Okay, in today's class, let's make a slight digression. So let's for the time being forget about the dynamic optimization problem or dynamic programming. Instead, let's look at two math questions that have some time-symmetric structure. And let's look at how exploiting such time-symmetric structure makes the problems easier. Let's start with the easier one. Consider the following geometric sequence. The initial term is 3, and after that, each term is half as large as the previous term, so that a sub t plus 1 is equal to 0.5 times at for all t. Denote by capital St the infinite sum of this sequence starting with at. So St is equal to at plus 1 plus at plus 2 plus dot dot dot. Compute S1. That is the sum of this entire sequence. Well, a common approach is as follows. By definition, S1 is equal to A1 plus A2 plus A3 plus dot dot dot. And by definition of S, the part from the second term on is denoted as S2, but S2 is just half the size of S1. And that is because the first term of S2 is half as large as the first term of S1. The second term in S2 is half as large as the second term in S1, and so on. All the terms in S2 are just half as large as the corresponding term in S1. And therefore, S2 is equal to 0.5 times S1. So we just have S1 equal A1 plus 0.5 times S1. A1 is equal to 3. Move this term to the left-hand side and take S1 common. And we have S1 equal 3 over 1 minus 0.5 equals 6. And this is kind of what I mean by exploiting a time-symmetric structure. When computing S1, we didn't actually sum up infinitely many numbers. Instead, we looked at S1 and noticed that some part of S1 is S1 again. S1 contains S1 itself. And by realizing that fact, the problem got much easier. Next, let's look at a slightly more complex problem. There is a roulette, and as you can see, on this roulette, there are 6 numbers, 1 through 6, in a clockwise order. All the numbers are equally spaced, so they realize with the same probability 1 over 6. The game proceeds as follows. First, you turn the roulette once. If the roulette shows 6, then the game is immediately over. If the roulette shows any other number other than 6, then you have to toss a coin. If the coin shows head, then move the roulette by one number clockwise, so that 2 will become 1, 1 will become 6, and so on. If the coin shows tail, then move the roulette by one number counterclockwise, so that 2 will become 3, and 3 will become 4, 4 will become 5, and so on. And you keep doing this, you keep tossing the coin and moving the roulette by one number either clockwise or counterclockwise depending on the outcome of the coin toss, until the roulette finally showed 6. Once the roulette showed 6, then the game is over. Question. Find the expected number of coin tosses needed before the game ends. Now I suggest that you pause here and think for 5 minutes before you see the answer. This game has lots of possible scenarios. The game might end quickly, or the game might last on and on and on. So you might have thought that this question involves lots of case divisions. But you might have also noticed that this problem has some time-symmetric structure. To understand this, suppose that the first time you turned the roulette, it showed number 3. What's the expected number of coin tosses you need before the game ends? Seems like a very complicated problem, but suppose that you tossed the coin 100 times, being unable to finish the game, and the roulette is still showing number 3. What's the expectation of additional number of coin tosses you need before the game ends? The same. The answer should be the same. As long as the roulette is showing number 3, how many times you have tossed the coin so far doesn't matter. The game has a time-symmetric structure in this sense. For this problem, using the concept of conditional expectation is helpful, although the original problem does not ask any conditioning. So let x be the additional number of coin tosses needed before the roulette first shows 6. So our goal is to find the expectation of x. Actually, we don't even need this word additional the first time roulette is turned. But anyway, we want to find the expectation of coin tosses needed. Also, let y be the number the roulette is currently showing. Let us introduce the notation mu1, mu2, up to mu6. So mu1 is the expectation of x given y equal 1. That is, mu1 is the expectation of the number of coin tosses needed before the game ends when the roulette shows 1. Similarly, mu2 is the expectation of x given y equal 2. That is, mu2 is the expectation of the number of coin tosses needed before the game ends when the roulette is currently showing number 2. And so on. We define mu3, mu4, mu5, mu6 in a similar way. Once we define these mu's in this way, these 6 mu's must satisfy the following system of equations. For example, mu1 must equal 1 plus mu2 over 2 plus mu6 over 2. Mu2 must equal 1 plus mu1 over 2 plus mu3 over 2, and etc. Why? Well, for example, what is mu2? The expected number of coin tosses you need before the game ends when the roulette is currently showing number 2. How many more times do you have to toss the coin when the roulette is currently showing number 2? Well, you have to toss the coin at least once again, so you have number 1 here, and after the coin is tossed, the roulette will be showing either number 1 or number 3. If the outcome of the coin toss is tail, and hence the roulette shows number 1, after that, the expected number of coin tosses you need will be mu1. If the outcome of the coin toss is head, and hence the roulette shows number 3, then after that, the expected number of coin tosses you will need is equal to mu3. And of course, those two situations occur with equal probabilities, half and half. Other equations are explained in the same way. And of course, mu6 should be equal to 0. Because once the roulette shows number 6, then the game ends immediately. Once you solve this system of equations, mu1 and mu5 are 5, mu2 and mu4 are 8, mu3 is 9, and mu6 is 0. So the unconditional expectation of x, that is the expectation before you first turn the roulette, is just the average of these 6 mu's, and it's equal to 5 and 5 over 6. So approximately you are supposed to toss the coin 5 to 6 times on average. Okay? I hope you got some idea about recursion from this example, because we are going to apply this idea to dynamic optimization problem in the next class.